All right, so we've now become familiar with the components of the AC power analysis, which are the apparent power, the real power, and the reactive power. And so now we can view them as they are meant to be viewed in the context of this thing called the power triangle. So I'm going to draw some axes here, because that's really what we're looking at, is we're looking at a coordinate plane where the y-axis is the imaginary and the x-axis is the real. Okay, and so we can represent this vector, right? This vector that points to this point in the complex plane here. We can write that as, its x value here is p, goes p in the real direction, and q in the imaginary direction. We can write this as p plus jq, which that's called the complex power, okay? So that vector representation in rectangular form is the real power, P, plus J times the reactive power, Q. And so if we take a look at this, we can note that the polar representation of that vector from the power triangle, right, the magnitude of this vector is the apparent power. That's S. Right? Well, we know what the apparent power is, so we can say that the magnitude of this vector is S, and we know that that's just VRMS times IRMS, right? And then we can say that the angle of S is just equal to, phi, which is phi of my voltage minus phi of my current. This is all from the perspective of the source, of course. That's what we've been doing this whole time. And so I can rewrite that my complex power S is equal to VRMS times IRMS. This is in polar form. Angle phi V minus phi I. And that right there is my complex power. And from this complex power and from this power triangle, really, everything that we've learned so far can be derived. So if we find the complex power, which really all we need to find the complex power is this particular vector, which comes from the RMS voltage of the source, the RMS current of the source, and the phase shift between the two signals. We can find the real power, we can find the reactive power. And so in order to fully characterize the power analysis of some system or circuit, really all we need are these values. And so it makes sense. This can be replaced with just phi. And so let's take a look at this. Hopefully you remember SOHCAHTOA from geometry, whenever you learned geometry and trig. But what that means is that the sine of an angle is equal to the opposite side over the hypotenuse of the triangle, right? Hopefully you remember this. Cosine is adjacent over hypotenuse and so on. But we're talking about this angle here, phi, that's this angle, the opposite in that case being Q and the hypotenuse being S, right? My right angle of this triangle is here. So this is the hypotenuse right here. And so from that, I can say the sine of phi is equal to the opposite, which is Q, over the hypotenuse, which is S. And so if I rearrange this for Q, I get that Q is equal to S times the sine of phi, which we know that's correct, right? S is equal to VRMS times IRMS. Note that this S with the arrow is a vector, and this S is not. This is the magnitude of this. So that's another confusing notational thing, but just keep it in mind. But if I take this S equals VS RMS or VRMS IRMS and plug that in here, right? Now I'm back to the equation that we wrote down previously for reactive power, right? IRMS, VRMS, sine of phi, and it's derived right from the power triangle. Okay, so let me go ahead and put a box around that. All right, and so what about real power? Well, again, we can look at SOHCAHTOA. We can say the cosine of an angle, phi, is equal to the adjacent over the hypotenuse, right? The adjacent in this case being the angle, or the side adjacent to this angle, which is the power P, real power, or the average power. And the hypotenuse is still S, so we can say that the cosine of phi is equal to the adjacent over the hypotenuse. And we can, of course, rearrange this for P, and we could say that P is equal to S times the cosine of phi, which, again, S is VRMS, IRMS, and we already know that this is the case. P is equal to VRMS times IRMS multiplied by the cosine of phi, and that's exactly the equation that we got when we looked at average power, right? So this is just showing that this power triangle is really all we need to fully analyze the AC power for any circuit or system. We can basically get the RMS voltage and current at the source. We can determine the phase angle between those two signals. And from there, we can find the reactive power, we can find the apparent power, we can find the real power, and we can fully characterize the system, okay? So this is the power triangle. This is the equations as provided from the textbook. I went ahead and screenshotted this slide just so the equations were all here in a concise format. This is from the SATIQ textbook, so just so that I SATIQ 5th edition. I just wanted to put this here in case you want to reference this slide, which has all the equations for when you're solving problems, for calculating the apparent power, the real power, etc., reactive power. Okay, and I've basically written them all and boxed them all throughout the slides too, but I just thought it would be nice to have them all in one spot in case you want to reference this slide. I'm not going to talk about this slide. There's nothing to really talk about, but I'm going to go ahead and wrap up this video, and in the next video, we're going to go ahead and solve an example problem, and then we'll be pretty close to wrapping up this part of the module, and we'll be moving on to three-phase circuits, okay? So I'm going to go ahead and end this video right here.